Hello. Here's a screencast on a topic that's important to us in the course. So it's important you watch this, and if you've got any questions about the screencast, you make sure you bring them up in class the next time we meet. But the topic of this screencast is functional limits. All right. So this means we're going to be taking limits of functions. So up to now, we've been taking limits of sequences. Today, we'll introduce functions into the business so we can start talking about ideas like continuity and differentiability and integrability. So today's the day that starts. So in the textbook, this is section 2 of chapter 4. I asked you to read the first section and the second section the last time we met. So that's where this is coming from. And I'm still continue to follow the author because I think he's great. I think his perspective is really neat, and it's really good for helping understand the concepts. And the way I'm going to organize the screencast today is that we're going to start with the concept behind functional limits. Why is it important? How did people want to try to do it? What was the weakness of that idea? And how do we fix it? Then I'll give you some definitions that we're going to work with, and then I'll work some examples with those definitions, and then at the end I'll prove a theorem that's central to the concepts in this section. Okay, so first we'll talk about the concept, then the definitions, I'll work through some examples, and then I'll prove a theorem. So remember what functions are. A function is a rule that assigns to each input a unique output. All right, you learn this in pre-calculus, you talk about it again in calculus, and it becomes just sort of the way we mathematicians think about ideas. We think of them from a functional perspective. We're not going to worry too much about functions and get too deep into what they mean or what they are or what they do, but this is the definition that we're going to take. And there are some kind of functions that we like. You know, we love polynomials. Right, we even like some transcendental functions like log functions. But historically, mathematicians made the mistake of assuming all functions were as nice as these. But there can be some really bizarre rules out there that still respect this idea that a function's a rule that takes each input to a unique output. But they don't have to look as nice as these functions do. Okay? And we just have to keep that in mind when we do our work. So let's start with the idea of continuity. Okay, in Calc 1, we say a function f of x is continuous at x equals c if the limit as x goes to c of f of x equals f of c. And what that means is that if we have a function, its graph has no breaks or jumps, and it looks kind of like this. So here's where f of c is, the value of f of c. Here's where c is. Okay, and this is the picture right around here, right? In that little area, that's what a continuous function looks like at a point, right? Nice and unbroken. So this definition here for what it means to be continuous took a long time to become articulated. And we currently, in our class, we're going to work toward understanding what this means right now. To this point, the only kind of limits that we have worked with are sequential limits. Right, so you get a sequence xn, and we can talk about how that sequence converges to a number. And the definition of convergence here relies on that n. If you look up at the definition of continuity, there is no n there. So let's tell a story about how we get from sequences to this other odd definition. Odd in the context of what we're working on right now. So what does continuity mean? So here's the definition we work with today. But what it means is this. If x gets near the value c, then the values of the function, so the values of f of x, get near the value f of c. Okay? So, how can we move this? What's a natural way to move this toward the use of sequences? Well, one natural way is to take this x gets near c, right? We could replace that with xn gets near c, right? Xn is a sequence converges to c, right? That's straightforward enough. So maybe then that would lead us to say that what this means, limit as x goes to c of f of x, means the limit as x, oh no. The limit as n goes to infinity of f of xn. Oh, yeah, so maybe this is a possible definition for continuity? Right, so if we have a sequence that converges to c, maybe we can say our function's convergent, or a function's continuous to c if f of c equals this. So that's a natural thing to do, and that's what mathematicians did try to do historically. But here's the problem. Okay, so we've seen this function before, the Dirichlet function, sometimes called the popcorn function. Right? It's the function defined to be 1 if x is a rational number and 0 if x is not a rational number. Okay? So yeah, we've talked about this before. If you wanted to graph the function, that would be pretty hard, because all the rational numbers would get plotted up here, and all the irrational numbers would get plotted down there. They'd look like two solid lines because the numbers are so dense in the real line. Okay, so why is this a problem? Well, remember, we're exploring this idea that the limit of f as x goes to c of f of x, we could define it as the limit as n goes to infinity of f of x of n, where x of n is some sequence that converges to c, right? So this is what we're trying to explore. So why is this Dirichlet function show us that there's a problem with this definition? Well, consider this. Consider we've got a real number c, okay? What if xn is a sequence of real numbers with xn converging to c, but all the xn's are actually rationals? Okay? Then what this definition up here would be saying is that the limit as x goes to c of f of x, okay, we're trying to use this definition, but because all my xn's are rationals, this value is just always 1. And so we'd be saying that the limit as x goes to the c is always going to be 1. Okay. But consider, on the other hand, what if my sequence, which I said are in the reals, not the rationals, the reals, that converges to C, but xn is in the irrationals. Okay? So both of these things can happen. Given any real number, I can find a sequence of rationals that converge to it, because the rationals are dense in the reals. But I can also find a sequence of irrationals that converge to it, because the irrationals are also dense in the reals. So both of these two scenarios can happen at the same time for the same number c. But in this case, if all the terms of my sequence are irrational, then this limit, or this purported definition for the limit, here my values of my function at all my irrationals are 0, so I'm taking the limit of a bunch of zeros, and I get 0. Okay. So the problem with this is that these two numbers are different. Okay, but what I'm saying is that they could happen at the same time. Okay, this means that this definition is not well defined. Okay, this up here doesn't make sense because I can find an example of a function where it gives me inconsistent results, and I want a definition that works all the time. Right? So once the mathematical community understood this, they said, okay, we've got to find a better way. Right? Phrased this way, we want this idea of a functional limit to be independent of how x gets close to c. In the previous example with the Dirichlet function, the answer depended upon how we chose those terms of the sequence, right? If we chose them all to be rationals, our limit was 1. If we chose them all to be irrationals, our limit was 0. Okay? What we want is a method to talk about functional limits that doesn't depend upon how we choose that sequence. Okay? It doesn't depend upon how the x's are chosen to get closer and closer to c. Okay? So, to phrase it maybe a little bit more arithmetically, we want this idea of a functional limit. So we want the limit as x goes to c of f of x to equal to L if and only if the limit as n goes to infinity of f of xn equals L for all sequences xn that converge to c. Okay, that's what we want. Our previous attempt failed. The Dirichlet function showed us that. This is where we want to head. Okay. So those are the concepts that we're talking about. Now, for some definitions. So let's let f be a function defined on a set of real numbers a. So it's a real valued function whose domain is a. And let c be a real number, be a limit point of a. So we say the limit as x goes to c of f of x equals L if, given any epsilon greater than 0, there is a delta greater than 0 such that when the absolute value of x minus c is between 0 and delta, and when x is in a, then the absolute value of f of x minus L is less than epsilon. Okay, so this is what we're going to take for our functional limit, the definition of a functional limit. A couple things just to point out to you, that the C has to be a limit point of a set A. If C is not a limit point of your domain, we can't define what it means to take a limit to that value. Okay? So this is an important part of the assumption of the definition. Another thing to just keep in mind is this right here. The 0 down here means x is not going to be equal to c. Okay? All right. So, what does this mean? Well, let's copy this over to the top of a fresh page. You can do it. So, the picture that goes along with this idea is this. So, if we have a function and there's a set A that's its domain, and C is a limit point of A, okay? It doesn't have to be L. It doesn't have to be f of c. Let's just call it L. Okay. What it means is that given any epsilon, so here's going to be L plus epsilon, and here's L minus epsilon. What happens is that you're guaranteed to be able to, so what I'm doing here is I'm going to look to see. Okay, so those should be straight, but they're not. So what I've just done here is I'm calling this distance here delta. So this is a c minus delta, and this is a c plus delta. Okay, so what this picture demonstrates is that for any epsilon, okay, I get an epsilon neighborhood around L, and that's what the yellow lines represent, this epsilon neighborhood around L. I can find a delta neighborhood around C, okay, that's what the orange neighborhood, or orange lines represent, this delta neighborhood around C, with the property that if I pick any x in that delta neighborhood that's different from C, I can go up and I can look at the function value. So let's go over and see what the function value is. Then that function value is going to be inside the epsilon neighborhood of L. Geometrically, this is what this definition means. So if as x gets close to C, f of x gets close to L, this is what's happening. Now, if I wanted to be super careful about it, we don't know, or we don't care, what's happening right at x equals c. So I'm just going to put a little question mark. We don't know what's happening there. But if this limit exists, everything else is going to look like this picture. And I'll make one more point. What it means is that the values of the function, they're all getting closer and closer to this value L from both sides. Okay? That's what it means for this limit to exist. So these ideas that I'm talking about right now, these are ideas that you learn in Calc 1. So this should all kind of feel familiar. We don't talk about these ideas in terms of epsilons and deltas in Calc 1, but we do draw these pictures, and we do give you this geometric intuition about what limits mean. But here in real analysis, we're going to layer on these epsilons and deltas because we love them. What I'll also point out is that we could use topological notions to define this. So I'm going to pick another color. So this interval over here, the epsilon neighborhood around L, right? We could call that epsilon neighborhood. And then this delta neighborhood around C, I could call this the delta neighborhood around C here. So I could rephrase this definition using topological language. Maybe I'll do that. Let me swipe over here. So using the language of topology, we say, what do we say? If F maps from a set of real numbers A to R, and if C is a limit point of A, then the limit as x goes to C of f of x equals L if for every epsilon neighborhood and epsilon of L, there is a delta neighborhood and delta of C for which if x is in this delta neighborhood of C and x is not equal to C, then f of x is in the epsilon neighborhood of L. So that's the topological way to rephrase that definition. And we may go back and forth. Sometimes the topological approaches are nicer. Sometimes the arithmetic approach, which is what we call the previous definition, is nicer. So let me show you how we use this in practice. So I'm going to take a second, start a new sheet with the old definition copied to the top. So through the miracle of editing software, will happen now. Okay, so I've copied the definition over. This is the original definition, the one that we're going to work with primarily. And let's do an example. So let's let f of x be 2x minus 3. Okay, and say just its domain is the whole real line. And let's let C be 4. And 4 is a limit point of the real line because we can find a sequence of reals that converge to it. So let's show, or let's prove using the definition that the limit as x goes to 4 of f of x equals 5. Okay. So that's what we want to prove. Let's show how we demonstrate this using the definition. So in the definition, we have an L, that's 5 in this example. The C we've said is 4, and f of x is 2x minus 3. So what do we need to show? We need to show that letting epsilon greater than 0 be given, we must find a delta greater than 0 such that if 0 is less than, okay, so x minus c, x minus 4 is less than delta, then f of x minus L, which is 5, is less than epsilon. Okay, so that's what we need to show. So let me copy this over. We're going to do some scratch work. All right, with that copied, here's the scratch work. So scratch work. So you've done stuff that's kind of like this before. We're going to take a look at what we want to prove. Okay, that's where we're headed. So let's look at this f of x minus 5. And we want to make sure we want to make it smaller than epsilon. That's our goal. That's why I underline that. Well, f of x is 2x minus 3. So that's 2x minus 8. All right, so let me draw your attention to this. This is where we have control. We've got control over the x's, and we can make this x minus 4 as small as we want. So if possible, I'm going to try to make something that looks like absolute x minus 4 show up in the calculation or show up in my scratch work. So let me go back down here. So notice my two terms here, they're divisible by 2. So I'm going to factor out a 2. And boy, howdy, look at that. Isn't that awesome? So this is the same thing as 2 times absolute x minus 4. So now I can make that as small as I want, right? I can make this smaller than delta. So, but we want f of x minus 5 less than epsilon. So let's make 2 delta less than epsilon. So what does that mean we have to do with delta? Well, delta needs to be less than epsilon over 2. Okay, so we're done with the scratch work. Let's continue the proof. So let me swipe back here. We started the proof here. So let's continue it. So let epsilon greater than 0 be given. We must find a delta such that that's true. Okay. Choose delta equal to epsilon over 2. Then for x, satisfying 0 less than x minus 4 less than delta, we have f of x minus 5 equals 2x minus 3 minus 5 equals 2x minus 8 equals 2 times x minus 4, right? So here we're redoing our scratch work. But absolute x minus 4 is less than delta. Delta equals epsilon over 2. The 2's here cancel, and I get epsilon. So I've just shown absolute f of x minus 5 is less than epsilon. So this shows the limit as x goes to 4 of our function f of x equals 5. And that's the proof. Right? It's a proof from first principles. We're using the definition of functional limit that we just introduced a few moments ago. Let's do another one. Prove that the limit as x goes to negative 2 of x squared minus 1 equals 3. Okay, so let's do some scratch work here. So f of x in this case is x squared minus 1. Right? L is 3, and our c in this case is minus 2. All right, so we want to show f of x minus L in absolute value is less than epsilon, right? So that's what we want. So what's f of x minus our L? Well, L is 3. F of x is x squared minus 1. So I get x squared minus 4. Okay. So if we want f of x minus L less than epsilon, what do we say about 2 or x and negative 2? So what's happening? Well, 0 is less than x minus c is less than delta. So in our case, that means 0 is less than absolute x minus negative 2 less than delta. All right, so here's where we've got control. This is what we have control over. So we want to see if we can rewrite x squared minus 4 so it involves an absolute x plus 2. Okay, but that's easy to do, right? Because x squared minus 4 is x minus 2 times x plus 2. And so we see right there. That's where we've got some control. We can make x minus or x plus 2 as small as we want. But the trouble is here, okay? If we're controlling x plus 2, does it mean we don't have control over x minus 2? And we've seen something like this before. The answer to that is no. It turns out if we're controlling x plus 2, we're making sure x is close to -2, then we have an idea. The values of x minus 2 in absolute value depend upon that. So let's look at that for a second. We can make delta as small as we want. So let's first make sure we choose delta to be less than 1. What does that get us? Well, if x plus 2 is less than delta, then we can say, from the definition of absolute value, x plus 2 is between minus delta and delta. But if delta is less than 1, I can do this. So minus 1 is also going to be less than x minus 2, and 1 is going to be bigger than x plus 2. So I'm going to subtract 4 from everything. So I'm subtracting 4 from the left, subtracting 4 from the middle, and subtracting 4 from the top. So that means minus 5 is less than x minus 2 is less than minus 3. So that means that x minus 2 is going to be between minus 5 and minus 3. So from this, we can say 3 is going to be less than the absolute value of x minus 2. It's going to be less than 5. And what I'm interested in is this, an upper bound for absolute x minus 2. So going back to what we had before, if delta is definitely less than 1, then this product of absolute values, on the one hand, I know I can make this second thing less than delta. But what the work I just showed at the top of this page means that is less than 5. So the whole product is going to be less than 5 delta. Okay. So what does this mean? Well, this means if delta is less than epsilon over 5, then 5 delta is less than epsilon, which is where we want to go in our proof. Okay. So I've got two conditions here. I've got this condition and I've got this condition. So I just want to make sure that when I choose delta, that I choose delta to be the smaller of 1 and epsilon over 5. Okay. So let's go do the proof. So we want to show that the limit as x goes to -2 of x squared minus 1 is equal to 3. Okay, so here's the proof. Let epsilon greater than 0 be given. Set delta to be the minimum of 1 and epsilon over 5. Then if x is a real number where 0 is less than x plus 2 is less than delta, then we know two things. First, x plus 2 less than delta means minus delta is less than x plus 2 is less than delta. Subtract 4 from everything. We get that. And so minus 5 is less than x minus 2 is less than minus 3. So absolute x minus 2 is less than 5. Second, f of x minus L, in this case, is x squared minus 1 minus 3. is x squared minus 4 is absolute x minus 2 times absolute x plus 2. But we know absolute x minus 2 is less than 5 from the above, and we know absolute x plus 2 is less than delta. But we know delta is less than epsilon over 5. Those cancel. So we've just shown absolute f of x minus L is less than epsilon. This shows the limit as x goes to negative 2 of x squared minus 1 equals 3. And that's the proof. Right? The proof is pretty dense, and it relies, for you to write up a proof like this, you've got to do the scratch work. There's a lot of work behind the scenes. And then you have to organize that in a way that convinces your reader that you've dotted all your I's and crossed all your T's. All right, so I'm going to wrap things up with a proof. And it's a proof of the theorem we're going to call the sequential criterion for functional limits. So it says, given a function from a set of real numbers a into the reals, and a limit point c of the set A, the following are equivalent. 1, the limit as x goes to c of f of x equals L. And 2, for all sequences xn in A with xn not equal to c and xn converging to c, we have f of xn converging to L. Okay? So we've got everything we need to prove this. This answers the question that we started with at the beginning. How do we define functional convergence in terms of sequences that's independent of the sequence you choose? Well, the definition we gave for functional convergence works. Here's the proof. So we're going to prove 1 implies 2. And then we'll have to prove 2 implies 1. That's what we mean by equivalence. The first statement is true if and only if the second statement is true. So suppose the limit as x goes to c of f of x equals L. This means for every epsilon greater than 0, there's a delta greater than 0, where if 0 is less than x minus c is less than delta, then f of x minus L is less than epsilon. Right? So we must show that for any sequence xn in A, where the terms of the sequence are different from C and the sequence converges to C, we have the sequence of values of the function converging to L. Okay, what does that mean? That is, we must show that for every epsilon greater than 0, there is an n in the natural numbers where if little n is bigger than capital N, then absolute value of fxn minus L is less than epsilon. Okay, that's just our definition of convergence of a sequence. Okay, so since the sequence has to be arbitrary, we're going to just start with an arbitrary sequence. So let xn and A be a sequence where none of the xn's are equal to C, but the sequence converges to C. And remember, we know what that means. We know what the definition of convergence of a sequence is. In fact, we just wrote it down for the sequence of values of the function fxn. So we want to deduce that the sequence of values now converges to the value L using the definition of functional limit. So let's let epsilon greater than 0 be given. Okay. We must show there is an n where if n is bigger than capital N, then absolute value of fxn minus L is less than epsilon. Okay. By the definition of functional limit, there is a delta greater than 0 with the property that if x is in the delta neighborhood of about C, and if x is not equal to C, then f of x is in the epsilon neighborhood about L. Okay, so this is using the topological interpretation of functional limit. Since the sequence xn converges to C, there is an n in the natural numbers such that if little n is bigger than capital N, then xn is close to C. So I'm using convergence of my sequence with the delta that's given from functional convergence, which we're not used to, but just make a note of that. So it follows from functional limits, that the absolute value of f of xn minus L is less than epsilon, i.e. fxn is in the epsilon neighborhood of L. Okay. This shows the sequence of function values converges to L, which is what we wanted to show, that 1 implied 2. Statement 1 implied statement 2. Okay? All right, done. Now we're going to prove the reverse direction, that the second statement implies the first statement. Okay? That is to say, if for all sequences in A whose terms are different from C and that converge to C, we have f of xn, the values of f of xn converge to L. So suppose that's true. We must show the limit as x goes to c of f of x equals L. Okay, that is, given any epsilon greater than 0, there is a delta greater than 0, such that if 0 is less than absolute x minus c is less than delta, then absolute f of x minus L is less than epsilon. That's what we want to prove. Okay. So let's prove this in the following way. So we'll suppose this is true, but let's suppose the latter is not true. Okay. Let's suppose that the functional limit of f of x is not equal to L. Okay, that means by negating the definition of functional limit, there exists some epsilon naught, which is positive, such that for all delta greater than 0, there is some x that satisfies 0 is strictly less than absolute x minus c is less than delta, and it satisfies absolute f of x minus L is bigger than epsilon naught. Okay, that's the negation of functional limit. So consider these deltas then. Delta sub n is 1 over n. So for each of these deltas, we can find some x. So let's pick it. So let's pick xn in the delta n neighborhood of C. Okay, where xn is not equal to C, and f of xn is not in the epsilon neighborhood of L. Right? So here I just phrased using topology what this says up here. Okay? So for each n, I can find a delta n and an xn that has this property. So this gives a sequence with the terms of the sequence converging to C, and with the terms of the values f of xn not converging to L. Okay? That is, this is a sequence that doesn't obey what we assumed was true, right? So this is a contradiction. Okay? Thus, the first statement must be true. And this proves the reverse implication, and that concludes the proof. So let's just go review that one more time, just the statement of the theorem. So it says the way we're defining functional limits using epsilons and deltas is equivalent to using sequences to define functional limits, as long as your sequence is an arbitrary sequence. Okay? So we'll be going back and forth between these two ways to think about functional limits. The first one is the way we learn about in Calc 1, and the second one is a way we really have the tools to think about for the first time here in real analysis. So that's what I wanted to tell you about today. Please make sure you understand this proof. It's very similar to the proof that's in the book, so use it to help understand what I did here, and we'll build on these concepts and facts as we move forward in the course. See you next time.